If we open the Power View and load our demo.foam, which is the folder file we have created, that will load all the mesh files, and we can clearly see the domain 0, domain 2, and the solid. So the three main regions we have created. And now we can use the VTK composite index to clearly see the mesh regions. So the three mesh regions. The top is the air block, solid block, and water block. Now we go to the second part of defining the physical boundaries according to the AS and energy equation, and submit the model to OpenFOAM to solve the problem. So look back again. So the main definition will be within the 0. So the 0 folder is used to store all the boundary conditions for each region. So the region I mentioned is shown here. So we have the air inlet, which has a velocity and temperature boundary, and we have the cold water, also the velocity and temperature boundary, and the outlet for the fluid and the of air and cold and water. So firstly, we need to define the velocity, right? So we go to the demo folder, we will find the 3 where the 0 folder has been created if you use the previous split region, and then we go to the domain 0 first. The domain 0, we will clearly find a CL2 region. So if I open this file, I would see the definition of the boundary conditions. So here, this is the boundary which is for the water. So that is domain 0, which is for water, has the inlet, outlet, we have the bottom wall, and so if I open here, again with the slides, so the water, we have the inlet, outlet, we have the bottom wall, and we have its front back because it's 3-dimension. And what importantly here is the domain 0 to solid, which is the interfaces between the water and the solid, right? So this is the main boundary. What we can do is just to create a new file. We can copy all these boundaries from the velocity, and of course you can copy previous, or you can directly just copy my file here from the slides, and in the velocity, this I can save it as u. So that is boundary we will use for the velocity. So velocity, we have the meter per second as our unit, and we define a 0 for all the regions, and we need to define all this according to the CL2 region. So the CL2 region is exact what we need to define for each boundary. So the water inlet, we have the 0.05. So right, so we have 0.05005 meter per second as a fixed value. Outlet, we use the 0 gradient, and the bottom wall, we think at its wall, so there's no slip, and the front end, because it is 2D, we will use the empty, right? So that's a U, and I will copy the P RGH. That is what we need to define for the pressure boundary, because in the CHT multi-reach simple form, it will calculate actually the P minus IH, which is absolute pressure, subtract the height of the fluid. So that will be, again, the inlet, we have the fixed flux pressure, outlet is a fixed value, we think it is atmosphere, we have the absolute pressure, which is 0, and the bottom wall again is fixed flux, and the others except the front and back will be the empty. Then I can save as PRGH, that is pressure, and for the other is pressure only. So the pressure only will be purely calculated based on the PRH. So most of the boundaries here will be defined as the calculated. So you can see it's calculated, and calculated except the final front and back face. So we save it as P. So and now the temperature. So that is most important or secondly important for our definition, because we need to point out that the inlet has a fixed value. So the inlet of water has fixed value, right? A fixed value of 293.15. So that is 20 degrees C, right? Or 20 Celsius. We now here use the Kelvin, so we save it as T. So we use Kelvin temperature here. And the inlet has such temperature, and outlet we will use the inlet outlet to let the OpenFOAM to calculate. We only give it the initial value as here, and we'll calculate it. And the domain to solid, there's very special boundary or temperature boundary for heat transfer called turbulent temperature red couple mixed. So this is the interface where the heat transfer between the solid and fluid. So we currently give a kappa method, which means the temperature gradient is based on the heat conductivity of fluid as a value with initial value, but then the solver will calculate the follows. And also the bottom wall, which is a wall, we think it is perfectly insulated, which means I need to apply a heat flux which is 0. I actually apply a very high, so I can use it's a high heat flux which is being applied. So if I have the uniform 0, that means we don't need to give any heat flux, so it is perfectly insulated. So that's the T. So that's mainly for the definition of the fluid of water. So I have all this defined. If I go to the folder, here, so I have the 4 boundary or physical boundaries defined for the domain 0. So next I will just copy this 4 and I will copy and paste it into the domain 2. This is mainly for the air region. But we know the air region, we have different boundary names, right? We have the air inlet. I will change here to the air inlet, air outlet, and the top wall, right? The top wall, and also the bottom, that's the top wall, and also the domain 2 to solid. So previously it's domain 0 to solid, that's water. Now it's domain 2 to solid. So I open the pressure as my first. So I don't need to define further because it is calculated based on the PRGH. So I will just have the PRGH defined secondly. Again, I just need to change the name. That's top wall, and that's domain 2 to solid, and front back. So don't need to do so much here for the PRGH and the T as well. So that's air inlet. But remember, we have changed, right? for the air, we have the inlet temperature of, I'll quickly go here. We have the temperature which is higher, which is about I didn't calculate here. So we have the temperature of 200 degrees. So I need to use 200 degree plus 273. So that gives me 473.15. That is the inlet of air, and I have the air outlet. I have the top wall, which is also insulated with the uniform, and then I have domain 2 to solid, which is also calculated between the interfaces. That's a T. I can define here, and finally I go to the U. Again, just change the boundary names to be air, and the wall is currently the top, and also the domain name is 2 to solid. And of course, we need to change the velocity, because the air have much higher velocity, which is 0.1. So 0.1 as our velocity, which is positive, and the cold water inlet is 0.05. Is that? So we can check both. So that's domain 2. Let's check the domain 0. That's U. That's 0.05. If I go here, so that will be 0.1 from here and 0.05 from here. So that will be have the minus, right? So we have the minus along the y direction. So that is minus 0.05. Okay. That is a definition for the physical boundaries of both domains. And now we need to define the boundaries, or the physical boundaries for the solid, after finishing the definition of the domain 0 and domain 2, which is for the water and the air. So go to the solid, we only need to define two boundaries. One is the pressure, the other is the temperature. So I can still copy the boundary of P and T from the previous definitions, but remember that is only for the fluid. So I will open the file. I would say there's 4 boundaries for the solid. They are the solid side, front, back, and solid to domain to 0, and solid to domain of 2. So now what I'm going to do is just copy the solid, and I still use calculated. That's fine. And the front, back still here. I just copy the solid to the solid to domain 0 and solid to domain 2. Remember that is for the pressure definition of the solid. So I will delete this. So we have four boundaries to be defined. And finally, we go to the definition of the temperature. Again, we have 4, and we can define the internal field, or we can use the temperature definition here. So the internal field, I can use both the air or the air or the solid. Now I use the solid boundaries, so I need to define all this to the solid boundaries. But remember, for all this, we need to use the interface to define as the solid to the domain 0 or solid to domain 2. So the front back still empty. I don't need the outlet. So and also for the solid side of the two sides, it should be like internal boundary, so I can use some like calculated for the solid side. So where is my definition of the temperature? So here, so the solid sides, I can use the calculated internal fields, and that's fine. And the solid to domain 2 and solid to domain 0 is calculated based on the internal field. So that will be alright if it is defined for all the physical boundaries.